Now I'll take a look at the magnetic force on a current carrying wire. We start off by considering a short segment of a wire with length L, and I'm going to put it in a magnetic field coming out of the page, so I have green dots showing that the magnetic field vectors are coming towards you, I guess out of the screen, and I have current going to the right, which means that the electrons are actually moving to the left, because remember, the current direction always assumes positive charge carriers. As the electrons move to the left, they generally move with something called the drift velocity. You probably saw something about drift velocity when your teacher was explaining how current was derived. And I didn't talk about drift velocity in that section of this grade boosting course just because it's a fairly simple idea that doesn't actually come up in many places. But this is one place where it does come up. The basic idea is that electrons, as they move, they'll end up going in all kinds of directions, but in general, the electrons, in this case, would flow to the left, and that represents the electric current. And in general, that average velocity, when you consider all of the electrons, is called the drift velocity, as they drift to the left because of the electric field that gets set up by some EMF elsewhere in the circuit. The key thing is that the electrons in the wire are moving to the left, and they're moving in a magnetic field, so they will feel a magnetic force. That force is perpendicular to the field and is perpendicular to the velocity. And from the right-hand rule, the direction of the force is actually down. I start with my fingers to the left, I curl them out of the screen towards me, and my thumb points up, but these are electrons, so the direction of the force is actually opposite, and the force direction is down. Speed is just distance over time, so the drift speed is going to be equal to the length L, divided by the time that it takes for an electron to go from one end to the other of this length L. Therefore, I can isolate t and express t is equal to L divided by the drift speed. And this is for all of the conduction electrons. So if I take a snapshot and there are 50 conduction electrons between the two blue lines, then t is the amount of time that it takes for the one that is farthest to the right to go all the way to the left. So in that amount of time t, all of the conduction electrons in length L will pass the left-hand bar. Then recall that the definition of current, I, is dq by dt. And then if we're talking not about an infinitesimal amount of charge and time, if we're talking about an actual quantity of charge and an actual measurable quantity of time, then I can just write this as the total charge divided by the total time. I can isolate q equal to I times t, which then lets me substitute in the time that I just solved for, L over the drift speed. Then I want you to recall that in terms of magnitude, the magnetic force is equal to q vb sine theta, and for the electrons that are moving in this current carrying wire, the speed v is the drift speed. And the charges that are moving are actually the electrons themselves, that's q. So I can substitute in for q and then realize that v in qvb sine theta is actually the drift speed. But then the speeds are the same thing. We have the denominator and the numerator, so we can actually cancel those out. And this simplifies down to the magnetic force, and this is on the current carrying wire, is equal to ILB sine theta. And this has exactly the same form as qvb sine theta, and it turns out that in general we can express this as a cross product. So the magnetic force on a current carrying wire is equal to the current times an L vector cross B, the magnetic field. And the L vector has the length L and it's in the direction of the current I. So in this case, the L vector is going to be to the right and it will have the same length as the length of the wire segment. And this is true for all wires that are carrying a current through a magnetic field.